Okay, I'm up to the last part here, and after I finish this, we are finished with explaining the RSA algorithm, and at the conclusion of this, I'll make some comments as to where this algorithm is actually used today. You might be surprised it's used in quite a few things that you probably have done in the course of using your personal computer or at work or something like that. Anyway, if we apply this procedure to two prime numbers, we will quickly see they have only one GCD and it's 1. So here's an example I found on the net. I wasn't going to manually go through several prime numbers, so I looked up a numerical example of RSA. And they are P equals 137 and Q equals 131. Let's check its Euclid table. That means we're going to see if there is just one common denominator, which is 137 divided by 131 equals 1.0, so on and so forth. You drop what comes after the decimal point. So they are coprime, they only share 1. Drop the non-integer remainder, and the only GCD they share is 1. So they are good primes to use. Now we're ready to compute the private key and public key using RSA. So we go back to the equation above. P equals 137, Q equals 131. So N equals P times Q, that's 137 times 131, and the answer is 17,947. F of X, plugging the numbers in, we have 137 minus 1 times 131 minus 1. That comes out to be 136 times 130, and the answer is 17,680. We now select the prime number E equal to 3. If we check GCD 3, 136 equal to 1, it is. In other words, there's only one common denominator, 1. You can look at the above equation and see why I plug that in. If we do the exact same thing for the other one, that is the GCD of 3, 130 equal to 1, it is also. And now comes the hardest part. Here we form the modulus called D. D is equal to the mod of f of x divided by e, which is equal to the mod of the number we calculated, which is 17,680 divided by 3, and the answer is 11,787. Now I must explain how this comes out like that. Alternately, this is written as D is equal to 3 to the minus 1 mod f of x, which is equal to the mod of 17,680 divided by 3. 3 to the minus 1 simply means that it's a fraction. And that equals 11,787. The interdivision of 17,680 divided by 3 is 5893. But remember, this is not simple integer division. If we take 5893 times 3, we get 17,679. If we take the original value we calculated, which was 17,680 minus 17,679, the difference is 1. And remember, that is what P minus 1 and Q minus 1 must equal, namely 1. So the modulus is saying take 5893 times 3, 3 is our chosen prime number, and minus 17,679, and it equals 1. So now we have everything to form our public key, which is N, E, and our private key, which is N, D. The public key pair is 17,947, 3, and the private key pair is 17,9411787. This would be the digital signature of the first sender. Notice 11787 is prime and hard to guess, and that is why it's the private key. Of course, In a real RSA algorithm, the prime numbers P and Q would be about 125 digits long, which, by the way, is a number that goes beyond named numbers. You'd have to use scientific notation to even describe that number. But notice the public key is P times Q, and it could be a non-prime number. It isn't in this case, but knowing that will never let you know the D, because D is the mod of the two prime numbers, each minus 1, and only share a GCD of 1. That gets near impossible to guess by brute force trying combinations. The larger the prime numbers, P and Q, and the exponent becomes. To get the receiver's public key and private key pair, you reverse the process, and I won't go into that. So that ends the description of the RSA algorithm. And I just wanted to add, if you're wondering where this is used, if you've ever gotten a PDF document where you could create a signature that can be used to send that, like for instance on your, perhaps you live in an apartment and you need to have a digital signature that you put to that document before you renew your lease, that's RSA. If you're filling out a form for a job or for an application, and again, you're given the ability to create a signature or something of that sort, again, you're using private and public key pairs, which in the background is actually using an RSA algorithm, much more robust one than the one that I've displayed here, but it's the same sort of thing. So you probably have used RSA in the past and not realize it. Thanks a lot. That's the end of this video. I think, as they say on YouTube, if you like it, thumbs up, and of course subscribe to the channel. Take care.